I will be talking the role of electron-nuclear coupling. Generally, when you solve Hartree-Fock and post-Hartree-Fock, you decouple them. You actually solve electronic Schrodinger equation. But if you neglect them, and there is no other way to plug in again for calculating molecular processes or chemical processes, you may have lot of problem. So here specifically I will show the role of electronuclear coupling in chemical reaction, basically chemical reaction. So now if you start a problem, I mean you must start somewhere so that everybody is catching up your lecture. So if you consider barium titanate, this is not the actual formula, you have TiO6 8 minus unit, and that 8 units are surrounded by each other, okay, like that. Now if you consider, there are many 15 normal modes if you consider 1 unit, and if you actually keep all other normal modes at the equilibrium geometry and except T1G, I guess X or whatever, and that you vary, it's a displacement vector, so it can go from minus to plus. So you can, what you read in the BSc class, that triply degenerate is here, okay, only at the equilibrium geometry. If you go around, you will get, this is D3H, this is C2V, okay, and they split like that, okay. So now let's say, at that geometry, somehow there, and if you want to excite the molecule from ground among the splitted states, from the ground to the excited, this degeneracy only at the equilibrium, then what happens? It goes there and roll. So as soon as it roll, then what happens? It faces the degeneracy. And this is the problem, unless your equation of motion keep all the information, how it roll at different electronic state, then it is giving wrong result. Okay. So what does it mean? That means this kind of excitation is called Frank-Condon transition, and that is a fixed nuclear geometry, and that is what is point group, and that is what is Hamiltonian commute with the symmetry elements of that group. Okay, that is what is called Born-Oppenheimer approximation. Now, if you allow the molecule to roll, this Frank-Condon transition concept actually deviates, and that is not point group, that is called molecular symmetry group. Something like symmetry elements are product of the traditional symmetry elements multiplied by the nuclear permutation multiplied by the rigid rotation. That's how the group elements are prepared, and that is what is called beyond Born-Oppenheimer. So that is the starting point to tell you, and this kind of going down energy is called Ian-Taylor stabilization. This kind of going, this minima is away from the equilibrium, that is called Ian-Taylor distortion. That's how you can think of what I am talking about. Now, if you go back 1937, Ian-Taylor model, they are physicists, they actually, Taylor was postdoc of Landau. So he started with 2 harmonic oscillator, 2-dimensional harmonic oscillator like this, picture wise. Now if you arbitrarily couple with a linear coupling and try to diagonalize this Hamiltonian, what you will get? You get the conical intersection, and the formula will be R root over plus minus KR. That means in the diagonal it will be added plus minus KR. R is equal to root over x square plus y square. If you plot it, so the conical intersection develop. That model was taken by Van Blake in 1939, just after 2 years, and he solved the hexa-aqua copper complex. Why? 2 of the axial bonds are longer than the equatorial bonds. The same, that is the model they have taken and solved the kind of Ian-Taylor problem in chemistry. Okay, and but one problem actually, that's what, if you take the cross section here, you get this. This is what Ian-Taylor distortion, this is stabilization, so on and so forth. Now one problem remained, that was 39 or 37, and that took 25 years, 1961, Longet Higgins. If you find the eigenfunction of that Hamiltonian and you get this eigenfunction, and they completely, it was waiting for Longet Higgins probably, and since, it is xy kind of thing in polar coordinate, if you move from theta plus 2 pi, you see if it is 0, cos 0 is 1, sin 0 is 0, and if you go 2 pi, then cos pi is minus 1 and that is 0. That means the wave function changes sign. Okay. So if you have a degeneracy, the nuclear wave function changes sign. That's the problem. And that problem nobody noticed up to 1961, and that was noticed by Longet Higgins, and then he could not weigh out to solve it. He multiplied a phase factor, and that is what Professor Satyamurthy was talking, geometric phase, and that kind of phase plus minus. Now you can see at 0, e to the power 0 is 1, e to the power plus minus I pi by 2 is minus 1, and then minus 1 multiplied by minus 1, and then it follows. Okay, it is a single valued wave function. Okay, now this is one part of the story. Now if you take and do excellent calculation at this junction of time, and that calculation may be, at the level of MRCI multi-configuration. If you take sodium 3 cluster and try to follow the conical intersection between the two E prime degenerate state, what you will get, that is, you have D3H conical intersection.
Do I have to do something? No, this is
D3H conical intersection and also C2V conical intersection. And if you make round and do adiabatic ab initio calculation, and then if you follow one conical intersection, there is no sign change. The dominant coefficient of the electronic wave function, you have to write in the scratch of the computer, electronic wave function. Okay, you have to write. And if you in cycle 2, there is, let's say, if you consider one conical intersection, there is a sign change. If you consider two conical intersection, I said C2V, there is also conical intersection, then you see there is no sign change, so on and so forth. So that means, one conical intersection make a sign change in the electronic wave function, another conical intersection do not sign change. So electronic wave function changes sign, as I said, nuclear wave function changes sign, you are in confused state. If you want to get out of this kind of confused situation, you have to go Born-Oppenheimer treatment. And that is exact, that's treatment. And that treatment says this is the molecular Schrodinger equation, this is the molecular Hamiltonian, which is sum of the nuclear kinetic energy operator and electronic Hamiltonian. And then this is the molecular wave function, which depend on both electronic coordinate and the nuclear coordinate. That is the total energy that is constant for a specific molecule or a chemical process. And then what they did, I would say, that is one of the finest, not just finest, it is not just genius, something beyond. They did it double perturbation. What kind of double perturbation? Normally you read in the class, single kind of perturbation. What is that? If they took the electronic Hamiltonian and expanded in a Taylor series around the equilibrium, and then they use the perturbation theory to get the first order, zeroth order, second order solution, and they consider the nuclear kinetic energy operator as a perturbation. Why it is a perturbation? The nuclear kinetic energy, you have 1 by 2 capital M. The nuclear mass is 1836 times minimum heavier than the electron. So that's why that can be considered as a perturbation. And then you again expand. If you do that with a switching parameter, electronic mass divided by the nuclear mass to the power 1/4. I mean, why this is kind of 1/4? This is the switching parameter in a perturbation theory they consider. Because, after fourth order, they find, you see, this is after fourth order, this is to the power 4. That means small m by capital M just. 1 by 4 is gone. So that is already 10 to the minus 3. That is a very small. So beyond fourth order, you need not to take the quantity. So up to fourth order, this expansion and all this thing, you can show that the electronic wave function and the nuclear wave function can be written as a product. Okay, and that is a extraordinary good exercise one can attempt. Now, what later they expanded is they actually take the electronic eigenfunction, what Soti was telling, that is a semicolon rather than a comma. So it means this n act as a parameter nuclear coordinate and electronic electronic eigenfunction multiplied by the nuclear wave function, and then you can write over the entire Hilbert space, and that is what is called Born-Huang expansion. And now I will go very fast. If you substitute the total molecular Hamiltonian Born-Oppenheimer-Huang expansion, this is the total Hamiltonian, electronic Hamiltonian plus nuclear kinetic energy operator. This is the electronic Schrodinger equation. You solve by Hartree-Fock and post-Hartree-Fock. Everything, if you substitute, you get the coupling between the electronic state. This is the nuclear wave function, this is the nuclear wave function, and this is the gradient coupling between the two electronic state at the first order and second order, and they are having the same relation, that kind of relation. If you substitute back, you get for the if there is a 4 electronic state couple, then your adiabatic potential energy surface are diagonal. If you neglect the non-adiabatic coupling term, then they are every separation you have del square. Otherwise, you have coupling, and you see the tau is a skew symmetric matrix and with a vector function. Okay, it creates a vector field in the molecular system. And also, Hellman-Feynman theory, if you take the electronic Schrodinger equation, take a derivative with respect to the nuclear coordinate, you can manipulate and come here. For a degenerate situation, you get infinity at the point of degeneracy or sim. But one of the interesting thing is that if you have a singularity, if you do then if you have singularity, then you have deep trouble. How to solve it? There is something Cauchy's residue theorem, that is basically 1890. That tells you singular function, if you integrate circularly, it gives n pi. You just take 1 by r dr d phi, and then you can see it gives 2 pi. So, and 1 by r is singular at r equal to 0. So that's that's the simple way of understanding. So now what happened with, you make use of that and you transform this a nuclear Schrodinger equation, something called adiabatic diabatic Schrodinger transformation, this kind of transformation, and you can transform under a condition which is called adiabatic diabatic transformation condition. Now entire thing actually is published as a package in GitHub. It available, you can download and use, and this is also interconnected with Molpro and Columbus. So you can calculate the non-adiabatic coupling term, you can solve this differential equation, and once you solve, you get the A, and the A and U is ab initio solved. So A is solved by this equation through tau, and then you can have the W, that is diabatic coupling. Okay, and the GitHub details are there. Now, in this, since my friend actually extensively worked in during the IIT Madras on the scattering problem, I wish to tell about scattering. Let's say 3 states are coupled and hyperspherical coordinate. They are very complicated way function of the helicity quantum partial wave quantum number, and if you these are for details, you can find the probability for the outgoing and incoming wave packet, and then you can calculate reaction cross section and the rate constant. All the details are there, and we have the own program. This is another different program we have that is doing 4-dimensional quantum mechanical calculation for A plus BC kind of reaction, where all details are there, kinetic energy evolution, time propagation by Lanczos, and then the fully parallel, and how parallel it is you can see with increasing total angular momentum you can see. Now ab initio potential energy surface and non-adiabatic coupling term, how these 3 atom reactions are modeled by 3 side length of a triangle, where this distance is diatomic distance. In hyperspherical coordinate they are written like that. Hyperspherical coordinate is some advantage because all the reactive and non-reactive channels are handled even-handedly. Don't get too much about it. I will be coming actual problem. So let us
Okay,
consider.
this is Sushanta here. Okay, can I speak?
Huh.
Can I intervene and speak?
Yeah,
Yeah, Sushanta here.
yeah.
Sushanta Mahapatra,
Yeah.
who worked on hyperspherical
Yes,
and
Professor
Jacobi.
Sushant.
Huh?
Please go ahead. Please go ahead.
Yeah, hyperspherical and Jacobi. You cannot get the product in hyperspherical. You have to do lot of battle with that mathematically. Okay. Yeah. My question that you asked, the non-adiabatic coupling. I did myself on a triangular system. Yeah, long back. I extended it, and then I saw the reactive scattering on a coupled potential energy surfaces. Still I do it. I like it. I love it.
Okay, so what is your question?
So I do reactive scattering on coupled potential energy surfaces. Now, earlier I could not do differential scattering. Now I do it. Okay. Now I do it.
Okay, can I?
You can ask
Thank you,
me.
Professor.
You can ask me any question you have on differential scattering. I'll answer to you. Okay.
Okay, so can I continue?
Yeah, sure.
Yeah. So what I did for first, generating potential energy surface for the first three, electronic state, S3 plus, and the very accurate experimental molecular beam cross section and rate constant and there. As for example, what are the process? D plus H2, it gives DH plus H, reactive charge transfer, so on and so forth. Experimental results are there, molecular beam cross section. And so therefore, all three electronic states potential energy surface first we calculate. So the potential energy surface, you can see where is the conical intersection. This is the entrance channel, this is the conical intersection, and it exactly matches with the earlier people calculated and predicted. And then also you can see that there is a global minima, and that also very accurately matches. Let me tell you, these are you can see that calculation at the MRCI and also PV 5Z. I mean, almost killed actually that kind of, because we are going to handle non-adiabaticity. So therefore, this is the non-adiabatic coupling term, and this is the transformation angle which we call geometric or topological phase, and that kind of angle that helps to couple different electronic state. How it coupled, I just remind you, is this A matrix is cos theta sin theta, those angles, that's how they are coupled, and that gives you potentially coupled Schrodinger equation. Okay, so you have the angles, all angles 1, 2, 1, 3, 2, 3, and then when you have the diabatic Hamiltonian, you calculate the cross section, and this is the reactive non-charge transfer process, and this is our result, and other results are like that. Experiment are this, and excited state reactive charge transfer, experiment are like that, and our theoretical result is this one. Okay, here experiment is not there, so this is only I have other result are here, but our result has to agree with experiment because the other two agree, there is no other process. Okay, so this is the trajectory calculation at present we are doing with partly that is called surface hopping. Actually we attempted for D plus H2. This is, I wish Soti to look for this is we publish in chemical physics. You can see that RNCT it works with full quantum and experiment. For RCT, this is the full quantum and this is experiment, but TSH doesn't work actually. Okay, so that we published that it doesn't work, and that is TSH is developed by Jan Tully or something like that. an A plus H2 system, and there are spin orbit coupling also there, A plus H2, and these are the process, and we develop, each potential energy surface developing, it takes 3 years, okay, and millions of points are generated, and then we do adiabatic diabatic transformation by beyond bound Oppenheimer theory and construct the diabatic surface, and while doing dynamics, we go capital J up to get the cross section less than equal to 45, where all partial waves are taken. Okay, so focusing on reactive channel, otherwise you go to the article and see the detail. So this is without spin orbit coupling. If you consider spin orbit coupling, but still the conical intersection are there, okay, between sigma and pi state, and this is the entrance channel, and this is the outgoing. So it is a exothermic reaction of A plus H2 producing HF. There the Young-Taylor coupling is there, the Rayner-Taylor coupling is there, because it is pi associated with Young-Taylor, 2 pi associated with Rayner-Taylor. This is the pin orbit coupling that is also included there. Of course, this is within approximate one particle approximation, whatever available, and this is very important, Soti, because you see, as you increase the k, how all the partial waves are important for a particular j, results are getting converges. So centrifugal approximation is not a good approximation. That is what we have shown. This is in between result, and that is the final cross section, and our result is the best agreement with experiment, and these are detailed, and some analysis we have done, and root mean square deviation and mean deviation, all other theoretical results are far below except our. Okay, so helium H2 plus, actually I and Michael Baer and Professor Sotumurthy work together. He has been working over this area for a long time, so we are really benefited, and actually we dare to enter this system because each system has its own. First of all, we calculate all the 4 electronic state diabatic surface. It takes maybe 3 or 4 years to calculate at the AVQZ level MRCI, and these are the process. But I will be talking only for the involving first 2 electronic state. This is something interesting happened. We could publish the surface in Journal of Physical Chemistry. It should be reverse way. We are actually very upset because it should be reverse way because dynamics is published in Journal of Physical Chemistry. That's not good. It should be published in JCP, but we could not at the beginning. So this is the thing Soti shows. Only thing, these are the conical intersection where between 2, 3, these are the sharp peaks are conical intersection. You can see it goes pi, 2 pi and 4 pi. So all indicate between the 4 electronic state are strongly coupled, and this is the result, Soti. So this is the experimental result, this is our theory result, this is adiabatic, so it doesn't agree. The last one I have been working, and it will take surface is already prepared, MRCI level surface, and where all the geometric parameters, this is the barrier and this is the saddle point, okay. So are correctly reproduced. Now we have constructed the diabatic surfaces and doing the dynamics, and this is the D3H conical intersection for that system, and you can see it reaches this is non-adiabatic coupling term, and this is Stewart-Althrup result, and adiabatic result is more or less agreeing, and this is Stewart-Althrup diabatic result. There diabatic is not so accurate, our diabatic, but we do not have lot of results because the results are progressing. Okay, so H plus D2 also we produce, and now we have to go, final checking is experiment, molecular beam experiment. This is the where I will end. One minor thing I want to tell, very important thing, this is the orthopara. So in orthopara, if you consider the singlet of H2, you have, this is the nuclear combination wave function. If you consider this is the, antisymmetric, this is the symmetric 3. Now, the total product is electronic, nuclear, transitional, rotational, vibrational. Except nuclear and rotational, since already you, while producing the surface, you already taken the antisymmetric wave function for calculating electronic potential energy surface. So that is taken care. Translation doesn't changes and vibration doesn't changes. Okay. So therefore, only change is nuclear and rotational. So nuclear can have two combinations, singlet or triplet, but final wave function must be antisymmetric. Now, if you consider rotation, e to the power I m phi pj m cos theta. Now, if you change for a rotation, theta to pi minus theta and phi plus pi, and if you substitute, you get minus 1 to the power j e to the power I m j phi. Now, if final have to be antisymmetric, so this is already antisymmetric. So, j to the power 0 can be ortho or para. That name I always forget. So it is okay. This is anti-parallel. Okay, so this can be considered, and when j is equal to 1, 3, something like that. So that's how if you progress, and this is a detailed working equation. Now, interesting rate constant. You see, if we orthopara ratio, experimentally it reaches to to 3, and we get a peak at 140 Kelvin. And this is the heat capacity of orthopara hydrogen. It gives also a peak at 140. Okay, and now why these two came? Came because when you are colliding H2 with H plus, then alpha or beta it can arbitrarily replace. So that gives 3:1 ratio. But that peak at 140, that is because of uncertainty principle, and because the energy, collisional energy is so little that it allows J equal to 0 to 1 transition, and that is because you are getting this, and it is experimentally first time we have shown that the same peak you can get at that point. Okay. Ozone, we are working very hard. One of the problem I want to tell that everybody the ozone ozone is very discussed about scientific community, because you get negative temperature. You are supposed to get negative temperature slope of the rate constant, but you are not getting when O is coming and hitting H2, because you are getting a barrier at the entry of O to hitting on the H2. But then you are not supposed to get any barrier, and the people have been trying last 4 decades. What we find out, you can get rid of that barrier if you include 4 electronic states, because these states are affecting here. Everybody is doing highest level of accurate calculation even at the MRCI on the ground state, forgetting all other 3. But as soon as they include, and we've proved there is a conical intersection, and you see now that is called reef structure, that is what we got. Now, summary, the main purpose is you have to, since you have degeneracy and seam between the conical intersection, when you want to study chemical reaction at the quantum cross section level and want to match with experimental cross section or rate constant, you have to include excited state, and not just include, since they are sophisticated effect, this effect not very broad or something like that. You have to include in a very accurate way, and then you have to study, and we have gone up to that. Michael Beer and Sotomuti are collaborator, and Varendas for this work, ANRF for research funding, and my students. Okay. Oh, these are the details of equation. Anybody ask question, then I will go there.
Thank you, Professor Adhikari, for a nice talk. Yes, we can have some questions now. electronic state
Hmm.
changes when you go to the excited state. When you go to triplet electron to the triplet state,
One question.
one has to. This
Hello, can you hear me?
I'm saying this for the students. Okay, orthopara. This nomenclature is valid for the ground state.
Satrajit, can you hear me?
Yeah, yes.
In the ozone potential energy surface, there is a reef. Okay. I could not get rid of it. Okay.
Yeah. Can
What is
you
the way?
ask? Can you
Do
ask
you
the
have any
question?
suggestion?
Can you
Don't
ask
rule
the
out-
question once
Yes,
again?
Some surfaces. Okay.
Hello. Can you ask the question once again?
I am asking the question once again. Can you hear me? First of all.
Yeah. Please.
Yes, we can hear.
Yeah. I am asking the ozone potential energy surface has a reef
Yes.
which we could not get out of it. We could not get out of it.
Yeah.
Even Don't ruler gave the surfaces.
Yeah.
It is there, still there. What is the way out? Tell me.
So the way out is that while calculating the
I am not
MRCI
listening to
calculation.
you. I am not hearing you.
Okay. Yeah. What you have to do, you have to, first, 7S singlet cash SCF calculation. That means first you have to do cash SCF calculation, and that cash SCF you have to take 7 electronic state. We have gone up to 13, and then we find out 7 electronic state is enough to make sure the first 4 are good enough, but still reefs will be there. Now after that you have to do MRCI not only on the ground state but including 4 electronic state, and then you have to do Davidson correction. Okay.
Satrajit, you are a good friend of mine, and then I know you understand me, I understand you. No, I'll tell you one thing. Today you are telling that no, I have to take 7 electronic state. Yesterday or day before, I was telling I will only take two electronic state. That is enough for me for NSCT, non-adiabatic coupling.
No, that is all right, but if you want to get rid of this reef structure, reef feature.
No, this is ridiculous for me. Okay.
The reef feature.
I don't know how do I solve it. If I can solve it, I'll solve it. But I am not sure that I can solve it.
No,
I think we can take this question later.
Yeah. But reef feature was there, and that has been discussed by this. You can see. Okay.
Do we have any other questions?
Okay, fine. You stop it here. We will discuss later.
Yeah, sure.
Okay.